Okay, so hello everybody. Welcome back to the seminar. For this week, we have the great pleasure of having with us Giuseppe Puglisi, who is assistant professor at the University of Catania. Before that, Giuseppe did his PhD at the International School of Advanced Studies in CISA in Trieste. He is an expert on cosmic microwave background of all sorts. And for that reason, he moved for his first postdoc to Stanford University and the Kavli Institute for Particles of Physics and Cosmology. That's where I've actually met Giuseppe, and I have a lot of stories for that, but most of them are a little bit inappropriate. So I'll skip. He then betrayed us, Stanford folk, and went to UC Berkeley to continue his work there, and he's been involved in a lot of very exciting CMB experiments, particularly for Berkeley was Lightbird, which is still waiting for. Then he moved back to Rome for a small period of time, and like I said in the beginning, he's now a professor at the University of Catania, which is also his hometown as well. So we're fortunate for us to know him that we can actually visit him now in there. So today he's going to talk to us about modeling the Galactic CMB foregrounds with supervised and unsupervised machine learning techniques. Giuseppe, please take it away.
Thank you, Yannis. Thank you, Carolina, for this great invitation. I'm really honored of this, and I apologize for not being there because it's one of my one of my items in the bucket list to come and visit Crete and Heraklion in particular. So yeah, sooner or later we'll be able to meet together in person. The other thing is, yes, as Yannis said, is a great pleasure to be there, to be here and talk with you guys. Also because of the friendship, I mean, with Yannis and Carolina, that is dated really, for a while ago. Yeah, as we were saying before. Okay, let's start. So as it's been said, yes, we really care about the cosmological CMB, the cosmic microwave background, because of the relations of essentially the observables that are connected to it, and in particular for the related to the inflationary era, and in particular, these anisotropies that we do observe not only in intensity but also in polarization are tightly connected with the quantum fluctuation that were generated at the time of inflation. So there is this so there are two kinds of perturbations. We say the scalar perturbations that are essentially, you should imagine, sort of density perturbation in the matter field, and they generate the temperature and the E-mode polarization anisotropies of the CMB. And then there is this kind of matter perturbations also. They generate tensorial perturbation related to fluctuations of the space-time metric, and so they are we refer to them as B modes for reasons that you'll see in a couple of slides. The holy grail of this context is essentially this tensor to scalar ratio, which is the amplitude, which is a free parameter between these the tensorial perturbation over the scalar ones, and you see from this formula below that estimating R, this tensor to scalar ratio, essentially we have a way to probe what is the energy scale of the inflation, and so we are probing 10 to the 16 gigaelectron volts. So how should we visualize these primordial gravitational waves? They are not really, so if you want this analogy, what we have observed so far, essentially they are really like point source gravitational waves, the merge of black holes. It's like a very beamed gravitational wave. I mean, because it's involving a specific location in the sky, whereas for for the quantum metric perturbations, the one from the inflation, here we should observe a sort of background, similarly to, if you want, to the cosmic microwave background. And so we refer to it like the primordial gravitational waves. And I like to stress that we were looking for something that are 14 orders of magnitude.
I guess we lost Pepe. Yeah, no, I've lost him too. Really. So let's wait, see if he reconnects.
I will resume.
Sorry. Okay. Okay. So I was saying we were here essentially, and so I was saying exactly about the CMB anisotropies. I was saying that these E modes are, as you can see here from these slides, 1% linearly polarized, and the reason why we call them E modes are because you see this gradient like the electric field. So the curl-less pattern that you see in this image, whereas the B modes are the current upper limits, which is lower amplitude with respect to the E modes. They are essentially showing a pattern like the magnetic field. That's why they're called B modes, and they are their divergence-less pattern in the polarization field. There is another source of B modes, which are the so-called gravitational lensing B modes, which are essentially produced by the intervening matter along the journey of photons, CMB photons, in particular CMB E-mode photons, that are essentially distorted through gravitational lensing into B modes. But we are able literally to distinguish between the primordial B modes and the lensing B modes, as you can see in these slides, where you see that primordial gravitational waves are essentially involving mainly larger angular scales. You see here the power spectrum of angular correlations from as a function of multiples, and so multiples of L of 100 essentially means order of the degree or super degree scales. So it's the orange circles that I am highlighting here. And whereas the lensing B modes are involving higher multiples like L of 1000, which corresponds to arc minutes and sub-arc minutes angular scales. So far, as you can see in this plot, where you don't see lower triangles, essentially means upper limits on there are no upper limits essentially on lensing B modes, and indeed we detected very well, but not there is upper limits instead for the primordial ones. And indeed, so this is the state of art for the R parameter, which is the tightly connected with that, where we are essentially considering are lower than 0.036, according to the best state of art data that we have to date. Okay, this is I hope you got an overview. Unfortunately, there was an interruption, but I'm trying to recover that very quickly and save time for our discussion. Okay, so what has prevented so far to detect the CMB modes essentially is that, as you can see in this slide, we want to measure this signal shown as a solid black line, and what is essentially overlapping together with the signal is essentially galactic contamination. So our own galaxy emits a polarized emission in the very same frequency regimes. Then there is instrumental noise, which is this green band, which was pretty high when we, for instance, for Planck data, and another nasty challenge, which is the systematic effects. This box, orange box. So for Planck, these were the challenges, and so far this has been also challenges for the ground-based experiments. So satellites and ground-based experiments are coping with this. These are the frequency maps produced by Planck, and as you can see, yeah, for instance, here you already can notice how the galactic plane emission, as I was saying, is pretty much acting as a foreground, to the background of the cosmic signal. And this is kind of pretty much overall the frequency bands. So from 30 gigahertz, lower frequencies where we have polarization over synchrotron, also up to the far infrared regimes where we have the thermal emission of the dust. Here you see exactly what I've already said. So essentially, we have we employed for Planck about 7 frequency bands to characterize and safely remove as much as it was permitted from the sensitivity of Planck the foregrounds, the galactic foregrounds, because we can exploit the different emission regimes, the different emission profiles, the SED, essentially spectral energy density. So you see synchrotron goes in polarization as a power law, whereas thermal dust essentially emits like a modified black body. And so it's the peak of this modified black body is around the terahertz. So CMB instead is a black body, very well measured, and so we can exploit these different difference in frequency scaling to recover the foreground maps as well as this background. Intensity signal, so the temperature, and in radio astronomy, intensity and temperature are the same. It's a bit messier. There are other foregrounds, but essentially, yeah, what we really look for CMB modes, essentially the situation is something like this, where this blue upper limits should essentially propagate all the way down up to 200-ish gigahertz. So this is the situation, but yeah, you see the difference in an order of magnitude is already very well shown here. Okay, so the emission processes essentially are tightly coupled, and the coupling is essentially the galactic magnetic field that is essentially the responsible of the synchrotron emission and the polarization of the synchrotron emission, but as well as the thermal dust. Thermal dust grains, so we suppose that the dust is made of these grains that are ellipsoidal. They align along to the orthogonally to the galactic magnetic field, and essentially they absorb the unpolarized starlight and then re-emit it, a polarized starlight in the visible, but they also can they emit also in the far infrared and in the microwave regime a polarized thermal dust emission. So this is but essentially probing the polarized emission from synchrotron and dust. Essentially, we are probing the plane of sky component of a magnetic field. I'm going very very fast here because I know that in fourth there is a very great team of people working on the visible component of star polarization, and I hope that we can have also some discussion about this. So perhaps I'm assuming that these concepts are pretty familiar with you. Systematic effects are nastier in a sense because they don't have dependence as a function of the galactic latitudes, but they are pretty much homogeneous for a given experimental probe. And you can see here these gray and black dot points in this plot, in the left plot, that are related to the systematic effects of Planck. So as a systematic effects, by definition, they are pretty much homogeneous and isotropic, almost isotropic in the sky. The other challenge, as I was saying, was the sensitivity, and this is a limit due to an experimental limit. So you see here what we were able to reach with the state of art of CMB experiments up to essentially in the past decade. So Planck was employing order of fewer detectors, order of 10 detectors, but from space, essentially since we don't have atmosphere, this allows to have pretty much correspondence to ground-based experiments. When the correspondence is essentially one detector in space corresponds to 100 detectors from the ground. So, and indeed, but we were able to compare the results from Planck and ground-based experiments similarly. The other benefit for the sky is for satellites is the fact that we have with the lack of atmosphere, we can access most of the frequencies, and but it's very costly, as you can imagine. So in the coming years, essentially, we are moving to order of 100,000 detectors, and this is essentially what we consider and we usually call the stage 4, the fourth stage of CMB experiments, where we claim to give an ultimate detection of R from the ground, which is essentially employing this very large number of detectors. And believe that this is essentially giving you an overview of what are the observation footprints. There are, here I'm showing Simon's Observatory footprints. That is another ground-based facility in Chile. And I'll give you also an overview of the Simon's Observatory here in this couple of plots. So you see two configurations that are shown. So as I said, 110 to the 5 detectors, multiple resolutions. We will employ several small aperture telescopes as well as a large aperture telescope, so about 10-meter telescope. We will have 6 order of multiple frequency bands. So, but where essentially atmosphere allows, and a similar essentially setup will be also employed in the South Pole, where essentially the South Pole Telescope SPT and the BICEP in Keck Array telescopes, respectively a large aperture telescope and small aperture telescopes, essentially will be combined into the South Pole Observatory. The CMB stage 4 is essentially a merger of these two efforts, observational efforts, SPO, the South Pole Observatory, and the Simon's Observatory, SO. And in particular, the takeaway message is that same setup, small and large aperture telescopes, but two different observing sites, Atacama and South Pole. Space mission, instead, there is the only on the market, essentially, experiments is Lightbird, which is a Japanese space-led mission. And there are involvement from several institutions and other space agencies like the one in Italy, in France, and in Canada. Okay, so for this is just to give you an introduction, but I want to give you now what is the contribution that that I gave in the community in the past, and it was to essentially, yes, employ, as I said, unsupervised learning technique to learn and auxiliarize and help essentially the component separation methodologies to remove the foregrounds. And so the challenge for us is that the foregrounds, both dust and synchrotron, the polarized foregrounds, their emission changes along the different line of sight that you observe. And when I say that these emission changes, essentially it means that the SED, the values of the spectral parameters of the SED could be different. So, for instance, for synchrotron, there could be a dependence as a function of the line of sight in the spectral index. So it's still a power law synchrotron, but it could be with different spectral indices. And this is actually something that perhaps it's easier to understand when we consider dust. Dust, indeed, could be, given the different contribution of clouds along the line of sight, there could be an effective temperature as well as a different spectral index of the dust emission. And so this is what essentially challenges the component separation algorithms. And so we claim that that with an optimal partition of the galactic emission, so we need to identify how to subdivide the full sky maps, like the ones that they showed from Planck, we can reduce the B-mode residuals solely due to the galactic foreground polarization. And so what I did was to employ the number of cloud maps that were produced by Gina Panopoulou, I believe that you know very well her, and Lens in 2020. So these are actually, they employed, detected the number of clouds along a given line of sight using H1 data. But you can imagine how, instead of using H1 data, perhaps with the future PASIFY data, how this would be a benefit for us. And so they publicly released these maps, and I, together with uncertainties. And so essentially what we did was to build up with a spectral clustering algorithm, to identify a sort of this optimal partition, as I was saying. And this optimal partition, which is the blue box in this slide, will be the ancillary data that will be used in the component separation algorithms to estimate the component maps. And when I say component maps, it means that we identify essentially synchrotron map, a dust map, and a CMB polarization map. So here you see in this slide the partitions that we have estimated with the spectral clustering methodology, and here yes, is a simulated data set. So we considered simulations to identify how bad was to estimate the residuals due to CMB polarization, due to galactic polarization. We didn't include CMB B-mode signal, and so, but simply just the polarization foregrounds. And we consider two instrumental setups, so Lightbird and the small aperture telescopes of the SO. So the interesting thing is that the results are shown in this slide, and in gray you see the level. The thick gray line is the level of lensing B modes, and then there are two black lines. One is dashed and the other is solid, referring to different values of the R, the tensor to scalar ratio parameters for primordial B modes. And the results are that we obtained that we really that shows the benefit of the number of clouds is these blue lines with the points that are connected. So this is telling you that the level of residuals, just due to the fact that we don't really we don't know the galactic emission within the patch in a certain sense. So our the degree of knowledge of our foreground maps is up to the level of the cluster patches, the domain patches. Essentially is showing a mitigation that is lower than the current requirements, scientific requirements, both for Lightbird and Simon's Observatory. The fact that essentially the blue and the orange lines are respectively for Lightbird and for SO, they are lower than the 10 to the negative 3 level of tensor to scalar ratio. So it's the solid black line. These instead the shaded areas are the uncertainties due to the instrumental noise. So it's something that is totally not related to the galactic foregrounds. So this is something very, very interesting. But we wanted to, and with Gina, we were wondering how this was if it was really a benefit of essentially due to the number of cloud maps, in a sense, how to understand whether it was a sort of how to understand that these number of clouds were monitoring essentially the dust emission. And so what we did was instead, so we came up with the clusters by, we flipped essentially the clusters in the northern polar cap. And so we employed, we called this a flip test. And so it means that we used the northern clusters for the southern maps in the galactic polar cap, and vice versa. And so you see that with the wrong clusters, which is the right column in these slides, we show a larger residuals, especially closer to the intermediate galactic latitudes, and not only. And so this means essentially that, yes, it seems that the number of clouds are literally tracking what is the expected behavior of dust emission. So they are helping the component separation. If you want, in terms of power spectra, B-mode power spectra, the dashed lines are the residual bias of galactic foregrounds when we did this flip in the number of cloud maps clusters. And so it shows a larger residual, so meaning essentially that we are mismodeling our foregrounds, we are misinterpreting the foreground emission. Okay, the other interesting thing, I don't know how much time we're left, perhaps you tell me, but I hope to be quick in 5 minutes so that we have time to chat. The other interesting topic that I wanted to share with you is on the modeling indeed of the Gaussianity of foregrounds. And so, as I was saying before, dust polarization is being very well, let's say, probed at the degree and super degree scales. But we don't really know how the dust polarization and similarly synchrotron polarization look like in the sub-degree scales and above. And this is because, and below, apologies. And this is because there was a strong contamination due to systematics and instrumental noise. Essentially, the best dust polarization map, full sky, is being provided by Planck. And Planck had a certain sensitivity, as I said, and a certain systematics that were essentially, after mitigation, were essentially still present in the maps. So this resulted into a lack of polarized dust templates at the resolution of, say, 8-ish arc minutes. Essentially, we had to mitigate further instrumental noise and systematics. We had to use dust maps at a coarser resolution, say 80 arc minutes. And so, and this is actually, we have information instead that indeed we expect dust emission to happen at these low, small scales, because we have indication of filamentary structures and cold clumps where the star-forming regions are. And so we essentially, those are kind of the strong features of what I mean non-Gaussian features at large multiples, say smaller angular scales. So the modeling, and so my effort in particular, is currently focusing on this, essentially to synthesize or inject artificial non-Gaussian and small angular scales into our templates of dust, which are rosy resolution templates. There is an approach that is being proposed by Andrei Frolov in 2019, which is to exploit this transformation, which is invertible transformation, to synthesize in a non-Gaussian way the smaller angular scales, and in the so-called small IQU quantities, as you can see here. So this transformation is employing a non-Gaussian, it's not linear, and therefore not non-Gaussian, and it's employing essentially the Stokes parameters, IQU, and P, capital P is the polarized amplitude. So with this invertible transformation, we're essentially getting, we can have these small quantities and then synthesize easily the smaller angular scales, and then transform back into the real quantities, the capital IQU, with the formula shown in the second line. This is the state of art, essentially. It's called the logarithmic polarization tensor formalism. And it's the state of art of the models that we have produced in the so-called Python Sky model, which is a public package used by CMB community, and to give a first attempt of injecting non-Gaussian small scales. And another attempt, which is dating back to 2021, is a collaboration work that Nicoletta Krakmalnikov and myself did to use generative adversarial networks to synthesize these smaller angular scales. And this, the reason is that, as you can see, the power spectrum in these bottom panels, the power spectrum both for EE and BB, for synchrotron and dust, respectively shown in red and in green in these plots, shows that essentially they are mostly scale invariant. So the power spectrum goes as a power law, and so this shows a sort of fractal-like structure. And so we exploited that to say we can give a network, a generative network, the possibility to inspect low resolution maps and high resolution maps where the data are clean enough, so not affected by the systematics and noise, to learn how to convert a low resolution map into a high resolution one. And so this is the result. There are several details, but I don't want to get into the weeds into this. So you see here, in this map, you see the mock, which is the middle panel here, the generated maps of dust produced by the GAN algorithm, and then we compare with in the rightmost panel of this plot, we compare with the Gaussian synthesized small scales produced with a different methodology. And so you see that indeed there are structures that are popping out that are pretty different, but they really look like what we expect, from the dust. We are able to recover the power spectra. And a student of ours, Yao Jian, prosecuted this work into the Force Plus maps, allowing us to go from 80 arc minutes to the Force approach. Force stands for foreground scale extender, but it is also an Italian word, which is force, which translates to maybe. So we don't really know how the dust look like. Maybe look like this. And so with the Krakmalnikov 2021 paper, we produced maps up to 12 arc minutes, and it's the middle panel. The leftmost panel is the Planck map at 80 arc minutes. And so you see how we are able to extend further to 3 arc minutes with the work that Yao Jian recently published. Okay, so yeah, exactly, to give you a sense of the 3 approaches that I was telling you. So there is this Gaussian synthesized small scales, the polarization tensor small scales, and then Force small scales. We do see that there are differences between the 3, but the filamentary structures are just reproduced only with the Force approach, with the generative approach. And the interesting thing is that power spectra are pretty much similar. So because power spectra, they are not directional, they essentially assume that there are Gaussian quantities in the input, Gaussian maps in the input, and so the angular power spectra don't pick up the differences that we do see visually, in these previous maps. So that's why we are going towards have a more descriptive way of the non-Gaussianities for us. For instance, using the Minkowski functionals, like for bidimensional maps, we mean area, the 3 Minkowski functionals, area of the domains, the perimeter of the domains, and the Euler-Calet characteristic, also said essentially referring to the number of the domains. And here, just to give you a sense, here we are comparing. You see that the red line, which is the red is the Force line, is the Force is produced from the is the Minkowski function produced from the Force maps, is showing departures from the Gaussian model, Gaussian small scales that are actually pretty much overlapping with the Paul tensor ISM3 model. So there is a level of non-Gaussianity, but it's surely departing with the GAN. So the takeaway message here is that the force approach is showing more realistically non-Gaussian features than other approaches. And similarly, if we employ the reduced wavelet scattering transforms, we do see clearly these departures, clearly in the generative approach, where with respect to the polarization tensor approach. And so it's a bit complicated, but there are departures of, so here you should compare the red shaded areas with for this the right the top right panels and the bottom left panel, and then and you see indeed that they are the profiles, particularly for the bottom left panel, they are totally different, and this is just coefficients evaluated from wavelet. And the benefit of wavelets, essentially wavelet scattering transform, is exactly to estimate the scales along a certain the correlation of different scales and in different orientations. Something that, for instance, with the power spectrum, the so-called spherical harmonic transforms, we can really do. Okay, so I think I can skip this slide and then go to the summary. I wish I essentially gave you the sense of what is the state of art in this moment. We need foreground tracers and H1 data, Faraday rotation, number of cloud along the line of sights. Pacify is what we really need, and will be super instrumental for to provide ancillary information for component separation or foreground cleaning techniques. We are equipping already these techniques with to leverage the ancillary data, and this is, for instance, example for with the clustering approach. And then the other thing that we are focusing is on modeling of community transmissions, and it seems that this could be done with the generative neural networks together with wavelet scattering transforms. With this, I hope yes, I hope it was clear. But with this, I thank you for the attention, and I'm happy to take any question. Thanks. Hope you're still there.
Thanks. Thanks, Pepe. Thank you very much. We are here. We are here. So let's see if there is any question from the online participants. I see. Yes, Yanis.
I mean, I have more general questions. So if people have science related ones, but anyway, maybe I could just start and people. So I was more wondering of what is the status of Simon's Observatory and Lightbird, and obviously, I'm more interested in the point sources too. So any comments on that?
Yeah, no, I forgot to mention that. Thanks for the question. So we are on science mode essentially. Simon's Observatory is being deployed, both the small aperture telescopes and the large aperture telescopes. Commission is over, and so we are essentially on track. So the small aperture telescopes are already taking scientific data, and you should expect in a couple of years to see the first results. Regarding instead the point sources, the interesting thing is that we are expecting on order of 200 blazars, radio blazars, to be polarized and be detected with SO. And the good news is that with the cadence of a week time scale, we can provide maps of polarization data, and so of these sources, 200 sources, and perhaps infer and assess if there is any variation of the polarization angle. Together with these maps, another effort that we are leading is to produce essentially to have a transient alert system that with this cadence of a week time scale, we can exploit and leverage SO data also for multi-messenger astronomy. So this is happening. Is a sort of SO is going to be paving the road for S4, as you can imagine, because S4 will be similarly providing maps with this very similar cadence, and its transients are part of the science products of the stage 4 experiment. But yeah, stage 4 essentially is on the time scale that is in 5-7 years from now at the moment. I hope I answered your question, Yanis.
Yeah, no, that's great. I was mostly wondering because you know that the news for CMB is 4 and not that great. But speaking of these point sources, while we mentioned this, I got a similar another question of how actually those point sources affect what you guys doing, especially the ones that are in the detection threshold. It's not.
Sì.
I'm assuming the ones that you can clearly see, can detect with high confidence that is not a problem. But what happens with the other ones?
Yeah, there are two. Yeah, I agree. Okay, I see your point. So the unpolarized sources. The polarized sources. There are two effects essentially. Polarized sources act as a sort of Poissonian noise in the maps, in the B mode maps. Because they are undetected, they essentially with lower threshold, and so we expect at a certain point sort of threshold and of noise residuals in the B mode maps, just simply due to the point sources, polarized point sources. The good news is that essentially, so we appropriately chose the sensitivities so that we don't reach this confusion limit, but our sensitivities simply the noise is larger than the noise is higher than this Poissonian one. It's something that at a certain point, yes, it's a trade-off because noise, the noise, I don't know how to say it better, but essentially, yeah, I mean, low frequency channels are usually lower resolution, so this limit is at lower. It's lower than the sensitivity requirements, and vice versa at high resolution. The interesting thing is that, and this is something I wanted to stress more, is apart from the Poissonian noise, which is essentially addressed, it's the correlation of AGN, like these blazars, into the large-scale structure of the universe. Say, if this blazar lives into galaxy clusters, and so they live in a sort of halo, dark matter halo, there might be correlations and leading into a bias when we mask all these bright blazars in the lensing estimators. So the B modes that are distorted because of the very same dark matter halos that are distorting B modes, but they are also populated by these blazars. So the current studies here, it's a pretty preliminary, but the question that we have, how are we sure that I mean, we are not injecting, by simply masking those blazars, we are injecting a bias in the estimator because of this masking, because of this correlation and a native sort of physical correlation between blazars living in the dark matter halos. I don't want to be very technical, but just to give you a sense, what this is, what exactly in the community, in the SO community, we are currently working on.
Cool. Thank you.
Thanks.
Okay. I don't see any other hand up. So I think we can thanks Beppe then again.
Thanks.
Thank you very much.